I think we do already understand how the limit of the slope of a secant is connected to the slope of the tangent, but we're going to formalize our work today. And using this formalization, we're going to be using limits to determine slopes of tangents. And there are going to be two approaches. These two approaches are fundamental in differential calculus, which means they're not unique to high school calculus. They would be in any calculus textbook. The first method, there's two methods. The first method is going to be talking about a point, and here's the diagram. We're talking here about a point of interest, which is at point P, and this diagram should look familiar to you. This is what we did when we found the slope of the tangent to y equals x squared at a particular point. But what I'm drawing here is not unique to y equals x squared. It could be any function. So what we have is a point of interest. It's at P, which is f, which is a comma f of a. A is a specific value of x. F of a is the y coordinate at that point. And the problem is, how do we determine that tangent line? What we've said is, if we pick a second point that's nearby, and you've done this, but we're formalizing things now. You pick a second point that's nearby called Q, and you calculate the slope of the line connecting P and Q. We call that a secant line. The slope of that secant line is not the slope of the tangent. It isn't. But what we have learned is that if Q gets closer to P, then when you calculate the slope of the secant, you will get something that's closer to the slope of the tangent. So this is the starting point for this. In the past, we've chosen point Q and we've found the slope of the secant line, and then we've repeated that process, right? Well, let's write out a general formula here. Well, we don't have to write out anything. It's in your notes. The general formula for the slope of the secant is f of x minus f of a over x minus a. This is not a difficult concept, because when you take a look at this, the slope from P to Q can be found using a triangle that has rise over run. The rise would be the difference between the y coordinates. Y of Q is f of x, y of P is f of a. So that's where the f of x minus f of a is coming from. And then the run, of course, is the difference between those two. So that's why we can say the slope of the secant is f of x minus f of a over x minus a. And what's, I think, important here is you have to be able to kind of come up with this on your own. So then we said, well, what's happening to the slope of the secant as Q gets sufficiently close to P? And what we learned is that as Q gets closer to P, the secant slope gets closer to the tangent slope. All right. Another way to look at this, though, is to say that as x approaches a, the slope of the secant approaches the slope of the tangent. So forget about Q and forget about P. When I take a look at this diagram, in order for Q to get closer to P, then x has to get closer to a. What I'm talking about here, everybody, is instead of talking about Q sliding around on the function, I'm just talking about x getting closer to a. Because if x gets closer to a, then Q is getting closer to P. And the slope of the secant is getting closer to the slope of the tangent. The question becomes, how close can x get to a? Well, it can get infinitely close. But it can't be on a. So how do we communicate what's actually happening here? We use limits. If the slope of the secant is this is the slope of the secant. And if that's getting closer to the slope of the tangent when x gets closer to a, then we say the slope of the tangent is the limit of this thing as x approaches a. So what this is saying, and I don't think I have this written in this version of this note package, is that the slope of the tangent is equal to the limit as Q approaches P of the slope of the secant. This is the slope of the secant. There's your limit, and this is the slope of the tangent. And I call this formula or equation 1. And what we're going to do today is we're going to do a problem using this formula, and then we're going to do the same problem using a different formula. And this formula has its place in a certain application in calculus. There's a use for it that the other formula falls flat. But the other formula has a bigger use in calculus where this formula falls flat. So they're both legitimate ways to find slopes of tangents. So complete example 1, which is on page 19, using this formula. Find the slope of the tangent to f of x equals 2x to the 4, where x is equal to 1. I just want to make sure, is your question the exact same as mine? Same function, same point? Okay. So there is no need to draw this. I think we defeat the purpose of coming up with formulas when you start to draw and dissect every single question. The formula talks about 2 points, P, which is a comma f of a, and Q, which is x comma f of x. So what are these 2 points? Point P is 1 comma f of 1. Because when I say x equals 1, I'm saying a is equal to 1. I'm saying the x coordinate of point P is 1. And I don't really believe that I need to show work here, but if f of x is 2x to the 4, then f of 1 is 2 times 1 to the 4, which is why point P is 1 comma 2. Now, well, I'll get back to that in a second. So that's point P. What is point Q? Well, point Q is x comma 2x to the 4. And I'll tell you right now, this example is not particularly difficult. It's not difficult at all, really. Keep in mind, if I give this to you on a quiz, you are not given the formula for the slope of the tangent. You have to reason this out. So what we would do here is we would say the slope of the secant is equal to 2x to the 4. Well, maybe I better do this first. Is equal to f of x minus f of a over x minus a. Which means the slope of the secant is equal to 2x to the 4 minus 2 over x minus 1. And I don't know if you remember, I hope you do, when we were finding the slope of a tangent by finding secant slopes that got closer to the slope of the tangent, this was the thing you put in your calculator and you kept putting in numbers that were closer and closer and closer to 1. Because believe it or not, at that point in time, you didn't know how to evaluate this at x equals 1. And you can't evaluate it at x equals 1. But now we can use the appropriate language, which is the slope of the tangent, is the limit as x approaches a of the slope of the secant. Which means the slope of the tangent is the limit as x approaches 1 of 2x to the 4 minus 2 over x minus 1. And evaluating that limit should really be like stealing candy from a tired baby. All that's involved here is a bit of factoring to get rid of that x minus 1. So I'm going back in time, back over the one-sided limits, which is kind of relegated to the back of the room right now. It's not important. To where we opened up the toolbox and we used things like rationalizing and factoring to simplify limits. By the way, if you do put in 1 for x, you get 0 over 0. Here's a very interesting thing. Do all limits exist? No. Does this limit have to exist? Yes, because it's a continuous function. It's a polynomial function. It goes on forever. It has no breaks in it, which means there is a tangent everywhere on this function, which means it has to exist because this use of limits is leading to something that does exist, namely the slope of a tangent. So what do we do here? This is the limit as x approaches 1. I can factor a 2 out. I can recognize that x to the 4 minus 1 is a difference of squares, so I can factor it. I can recognize that the x squared minus 1, which is one of the factors of the x to the 4 minus 1, is also a difference of squares. Thereby eliminating the meddlesome factor that's causing me a problem. And again, this is just the way limits work. Even though 1 is a non-permissible value of that expression for the secant slope, we evaluate the limit by putting it in. So now I can go ahead and put this in. As soon as I do put in the 1 for the x, I am allowed to drop the limit symbol. And by my ciphering, I get 8. Good? 2 times 2 times 2. Were we asked for the slope or were we asked for the actual equation? We were asked for the equation of the tangent line. So this is the slope of the tangent. Don't forget that the point slope formula is what I would highly recommend whenever you were asked to find the equation of a tangent line. So we go y minus y1. Don't forget the point. I'm pretty sure it's 1 comma 2. So we put 1 in for x1, 2 in for y1, and 8 in for the slope. We end up with y minus 2 equals 8 times x minus 1. And, simplifying that and rearranging it is junior high-ish math. Better make sure I don't screw it up. I mean, I could from time to time. Don't get me wrong. I would just trounce a grade 8 students in a math contest. But 8x minus y minus 6 is equal to 0, I believe. Anybody else in agreement there? Whew. Okay. Now, I want to point something out to you, and this is just for later. And this, again, I think the examples we do today are fairly easy. The problems you're going to be working on kick things up a notch. Very often, instead of the question saying where x equals 1, they will say at 1 comma 2. Okay? And some students will go, I don't know what to put in here. Because in our example, we've calculated f of a by putting 1 in for x into the function. If they're giving you the point, 2 is f of a. Right? They're actually giving you the y coordinate. You don't need to calculate it. So don't let that confuse you. Does anybody have any questions with the work we did in example 1? And this is a by far more superior method because later on, I guess it's not going to be until Tuesday of next week, we will learn that equation 1 just falls flat. It doesn't do what we really need to do at some point. So what we do here is we still have point P and we still have point Q. And P is still the fixed point and Q is still a mobile point. But rather than calling the x coordinate at Q x, what we're going to do is call it a plus h. I'm just saying that h is some number we've added to the x-coordinate of p to get a new x-coordinate. And you may notice that we've done problems with limits with h's, and that's why you kind of get accustomed to seeing the h. This is where it's going to come from. So what are the coordinates of point Q? Well, the x-coordinate is a plus h, and the y-coordinate is f of a plus h. And what's interesting here is that there's no reference to x. There's no x in here. It's all about a. The same thing is true, that the slope of this secant line, however we calculate it, is different than the slope of the tangent line. Still true. It's still true that as point Q gets closer to point P, the slope of the secant line will still not be equal to the tangent slope, but it will get closer. These things are all still true. But the slope of the secant line is found differently. The slope of the secant line will be f of a plus h minus f of a over a plus h minus a. Let me show that to you. If I draw my triangle on here, and this triangle is not in your notes on your diagram, the base of this triangle has a run of the x-coordinate of Q minus the x-coordinate of P. It's x plus h, pardon me, it's a plus h minus a. The rise would be the y-coordinate minus the y-coordinate, which would be f of a plus h minus f of a. So that's where this is coming from, except a plus h minus a is simply h. And if you think about that looking at the diagram, what is the distance between a and a plus h? H. You're adding h to a to get to the new place, so the difference between them is h. The distance between them is h. So the two x-coordinates are separated by h. The top here I double-clicked by mistake, but the slope of the tangent will still be what the slope of the secant approaches. But if Q gets closer to P, I want you to think of this visually. If Q gets closer to P, and this is a fixed point, and this distance is h, then as Q gets closer to P, h is getting closer to 0. And that means that this equation for the slope of the secant, that's our h. If we take the limit as h approaches 0, we'll get the slope of the tangent. So I'm saying this, that the slope of the secant is equal to this, but the slope of the tangent is the limit as Q approaches P of the slope of the secant. But how is Q going to approach P? H has to approach 0. So that's where that formula comes from. And I like to call this formula 2, which again has better applications later on, this second formula. So what we're going to do is we're going to do the second example will be the same thing that we did in the first example, but use the second formula. And once we find the slope, we're going to get a slope of 8. We won't need to find the equation because that we've already done. It doesn't matter which method we use. So what is A? A is equal to 1. And that means that our formula becomes the slope of the tangent is equal to the limit as h approaches 0. This is a huge get for us in terms of a limit formula. It doesn't make reference to x. It's a limit as h is approaching 0. It has nothing to do with what x is doing. Of f of 1 plus h minus f of 1 over h. So what is f of 1 plus h? Well, don't forget, in this example, f of x is 2x to the 4. So f of 1 plus h is 2 times 1 plus h to the 4 minus 2 times 1 to the 4, which is 2 over h. And I just have to ponder whether I want to go down a path here or not. Just give me a second. Sure. I'm not going to expand out the minus 2 times 1 to the 4, although that's child's play, right? It's 2. It's minus 2. I'm going to get you to recognize that in the numerator, there's a common factor of 2. And you would definitely see there's still a common factor of 2 if you multiplied out that 2 times 1 to the 4. But what if it was 2 times 3 to the 4? You wouldn't see it. I also want you to notice that we're evaluating this limit as h is approaching 0, and if you put h equals 0 in the expression, you will get 0 over 0. So we have to do our magic to get rid of that h in the denominator. But if I factor the 2 out, I'm going to have 1 plus h to the 4 minus 1 to the 4. And I know that you know I'm aware, and you're aware, that 1 to the 4 is 1. Okay? I know you could write 1. I'm trying to make a broader point here. And the broader point is, what if, and there's no need to change things. Don't erase anything. What if a was 3? Well, then you would have the following. And the best way to work with this is to see that it's a difference of squares and to factor it. So whatever this thing to the 4 is, figuring out what it is as a number isn't going to matter because you're going to factor it as a difference of squares in this case. There is so much going on here with this discussion we're having about where to proceed here that there are a couple of other things I will mention in a second. So now we're going to factor this into 1 plus h quantity squared minus 1 squared and 1 plus h quantity squared plus 1 squared. And this is over h. The first major factor on the top is also a difference of squares. I'm really starting to lean here in terms of my writing. The limit as h approaches 0 of 2 times 1 plus h minus 1, 1 plus h plus 1, and then this part, which is 1 plus h quantity squared plus 1 squared over h. Well, finally, what we have is this. One plus h minus 1 is h, so we have a factor of h in the numerator and denominator that cancel. Our wish has been granted that we've gotten rid of the h in the denominator. Now I can put 0 in every place there is an h. So I have 2 times 1 plus 0 plus 1 times 1 plus 0 squared plus 1 squared, which gives me 2 times 2 times 2, which gives me 8. So the slope is 8 no matter how you cut it.